Hi. For our EE 475 project, we reviewed and evaluated SNet. Anonymous provides deep learning method for correcting susceptibility artifacts in EPI imaging, published by Dong and colleagues in Magnetic Resonance Imaging in 2020. In this presentation, we will cover the problem, the classical top-up baseline, how SNet works, what we contributed, our results, and a brief code demo. So echoplanar imaging, EPI, is the workhorse of both diffusion MRI and functional MRI because it captures an entire 2D slice in a single TR. But the trade-off for that speed is geometric distortion, local B0 inhomogeneous at air tissue interfaces, the sinuses, the ear canals, the brainstem, cause off-resonance frequency shifts. Over a long EPI readout, those shifts accumulate into voxel displacement that can exceed 5 to 10 voxels in the worst regions. If you don't correct them, downstream analysis like DTM metrics or fMRI activation maps end up systematically biased. You can see in this image how the same brain looks geometrically different when acquired with two opposite phasing code polarities. That's the artifact we want to fix. So the key physical insight is that the distortion along the phasing code axis is proportional to the local off-resonance and the readout time, as shown in this equation. Crucially, when we reverse the phase encode polarity, the displacement reverses sign, same magnitude, opposite direction. So if we acquire the brain twice, once with flip up polarity and once with flip down, we get two images that show the same anatomy but with opposite distortions. The diagram shows the common anatomy P distorted by plus U to give the blip up image and by minus U to give the blip down image. The correction problem is then, given these two distorted images, estimate the displacement field U and recover the underlying anatomy. This is what top-up does and what SNet does. They just go about it very differently. So top-up, introduced by Anderson and colleagues in 2003, is the clinical reference for this problem. It formulates correction as a nonlinear optimization find the field that minimizes the square difference between two unwarped blip images with a smoothness regularizer. Four design choices matter. First, the field is parameterized as a cubic B-spline, which gives implicit smoothness and far fewer parameters than a dense voxel field. Second, the optimization runs hierarchically on a multi-scale pyramid, coarse to fine. Third, it uses iterative Leavenworth Marquardt with alternating updates for the field and per volume motion parameters. And fourth, most importantly, the Jacobian term J, brighten compressed regions and dim scratch ones. So signal is conserved across the correction. This is the intensity modulation step that SNet will turn out not to have. Top-up is accurate, well-validated, and clinically accepted. The downside is speed. On our test data, a single 160 by 160 by 104 volume took 12 minutes and 14 seconds on a modern MacBook CPU. For a single research subject, that's fine. For a population study or real-time scanner site preprocessing, it's prohibitive. That's the gap SNet tries to close.
SNet's idea is conceptually simple. Replace top-ups per subject optimization with a single neural network forecast. The architecture has two components. First, a 3D unit takes two blip images concatenated as input and output a smooth displacement field of the same spatial size. Second, a spatial transform unit, or STU, takes that field and the original blip pair and produces the two unworked images using differentiable trilinear interpolation. The STU is the same kind of building block used in voxel morph for medical image registration. Once trained, an interference is just one forecast, milliseconds on a GPU. That's the speed promise. The question is how you train such a network, given that we don't have ground truth distortion-free images. The answer is to train unsupervised. The loss has two terms. The first is the local cross-correlation LCC between two unworked images. If the network has predicted the correct field, both unworked images should look like the same underlying anatomy, so they should be highly correlated. The second is a diffusion smoothness regularizer on the predicted field, with a weight lambda that we set to 0.01 following the original paper. Critically, this loss requires no ground truth and no paired training data. The network just needs the blip pair itself. In our case, we train subjects specifically, meaning we trained one model per scan, effectively overfitting the network to a single pair. The plot on the right shows our actual training loss for the 3D variant, smooth monotonic decrease from 0.84 to 0.62 over 500 epochs, taking about 14 minutes on a Tesla T4 GPU Nikolai. Now here's where we did something beyond just running existing code. The SNet constructor in the public repo advertises that it supports three displacement field dimensionalities, 1, 3, or 5. The physically correct choice is 1, because susceptibility distortions are along the phasing code axis only. By physics, that's the Jezard and Balaban results from 1995. A one-channel field encodes a physical prior. A three-channel field allows a network to predict unphysical displacement in non-PE directions. When we tried to instantiate the 1D variant, the code crashed with a key error STU1D. It turns out only the 3D STU is actually implemented. The 1D and 5D options are advertised but never coded. This is a latent bug that's been in the repository for 5 years, so we patched it. We implemented STU1D from scratch, about 50 lines, which takes one channel field, adds zeros for the non-PE axis, and reuses the existing interpolation pathway. This is fully documented in our patches.md. The implication is that every prior user of the code base was silently forced in the 3D variant. To our knowledge, we are the first to compare 1D versus 3D parameterizations under identical training conditions. Briefly on setup, the data is the SNet author's public example pair. One HCP style diffusion EPI scan with reverse phase encoding at 1.5 millimeter isotropic resolution. We acknowledge that one subject is a real limitation. Top up we ran with FSL 0.0 default configuration on a MacBook CPU. SNet we trained for 500 epochs of Adam at learning rate 0.001 on Colab T4 GPU, with identical hyperparameters for both 1D and 3D variants to keep the comparison clean. On the right are the 4 code level changes we had to make to get the 2020 repository running on modern Python. None of them affects the science, but the original code is unrunnable on a fresh install today.
Here are the quantity results against top-up as the reference, compute inside and also derived brain nest. The first important point is that the raw SNet PSNR looks extremely poor, 6.14 dB for both 1D and 3D. But this is misleading. SNet uses local cross-correlation loss, which is invariant to global intensity scale. So network can produce geometrically corrected images at an arbitrary intensity level. After fitting one global gain and bias inside the brain mask, the PSNR improves to 19.4 dB for 3D and 18.48 dB for 1D. Second, gradient SSIM stays high around 0.8, which shows that the anatomical edge structure is preserved. Third, inference is extremely fast, around 0.13 to 0.14 seconds, compared with 738 seconds for top-up. So the feed-forward speed-up is about 5,000 multiplier. But since subject-specific training also took around 14 minutes, the speed-up matters mainly when training is amortized across many subjects. Qualitatively, SNet reproduces top-up-like geometry. The corrected images preserve ventricular structure and gray-white contrast, and we do not observe folding artifacts. The residual errors are mostly concentrated around high-contrast edges, such as cortex, ventricles, and eye region. This is consistent with subvoxel registration disagreement rather than a complete correction failure. The predicted displacement field is spatially structured, not random. In this single subject example, the 1D and 3D variants behave similarly, so we cannot claim a strong qualitative advantage for either one. A multi-subject study will be needed for that. The demo shows 3D and 1D training for SNet on Colab. It saves the corrected outputs. Also, it shows the training and interference forward fast times. Then, on the Mac terminal, we run evaluate pi to compute PSNR, SSIM, gradient SSIM, intensity matching, and report figures shown for 3D and 1D pipelines. Evaluation shows 18.48 dB for intensity match PSNR, 0.84 for SSIM, and 0.8 for gradient SSIM. The interference speedup is about 5,000. To conclude, SNet has 3 limitations. First, the LCC loss causes intensity scale ambiguity. The geometry can be corrected while the output intensity scale is wrong, so post-hoc intensity matching is needed. Second, unlike top-up, SNet doesn't include Jacobian intensity modulation, so signal conservation is compressed or stretched regions is not explicitly enforced. Third, the loss compares the two unwrapped images to each other, but it does not require the corrected image to forward distort back to the actually acquired API data. This is the key limitation addressed by the FDNet. Overall, SNet is a strong, unsupervised, and very fast alternative to top-up at population scale, but for one-off subject-specific correction, the training time reduces the practical speed advantage. Thanks for watching. We are happy to answer any questions in the interview.